4,000 API calls. Minutes. That's how fast a poorly architected AI agent can torch your production budget before a single human notices. I'm not talking about a hypothetical. This happened on a real system, an automated customer support pipeline where a Claude agent was given a retry loop with no hard ceiling. The task looked simple. Parse an incoming ticket, classify it, route it. But the agent misread the loop termination condition, decided it hadn't completed the task, and re-invoking itself. Each cycle spawned 2 more tool calls. Exponential. By the time the PagerDuty alert fired, the AWS Cost Explorer graph looked like a vertical cliff. The on-call engineer thought it was a billing dashboard bug. It wasn't. Here's the brutal truth. The code's clean. The prompt was well written. The agent was doing exactly what it was designed to do. It just had no architectural guardrails telling it when to stop. And that's the trap. Not the AI. Not the tool. The architecture decision made 3 weeks earlier in a Notion doc nobody reviewed twice. By the end of this lecture, you will have a concrete decision framework to make sure this never happens on your watch. Right after incidents like this go public in engineering Slack communities, you always same thread appear. Someone posts, N8 is dead. Claude managed agents make workflow tools obsolete. And then the counter-argument, agents are unreliable black boxes, just use N8 for everything. Both sides are missing the point entirely. This is not a tools debate. This is an architecture paradigm debate, and the two paradigms have fundamentally different failure modes. The N8 is dead crowd is picking a tool before they've defined what kind of system they're building. Are you building a deterministic pipeline where every step is known in advance? Or are you building a reasoning system where the path to completion is discovered at runtime? These are not the same problem. Treating them as the same problem is exactly how you end up with either a Talo, Pebble runaway agent, or a 400-node N8 workflow, so rigid it breaks every time the upstream API changes a single field name. The wrong framing is, which tool wins? The right framing is, what does my task actually require? And that's the question we're going to answer with a real decision framework. Starting right now, let me tell you exactly what you're going to walk away with from this lecture, because I hate courses that promise frameworks and deliver PowerPoint platitudes. By the end of 6 chapters, you will have a 3-axis decision matrix that you can apply to any automation task in under 5 minutes. The 3 axes are: task complexity, is the execution path known in advance, or does it need to be discovered? Determinism requirement, does the business need 100% to reproducible output, or is best effort reasoning acceptable? And operational cost sensitivity, what's the cost profile per run, and what's the acceptable blast radius if something goes wrong? Every automation task you will ever design sits somewhere in this 3D space. The matrix tells you which architecture quadrant it belongs to: pure workflow, pure agent, or the hybrid pattern that handles 80% of real production use cases. No more gut feeling tool picks. No more let's just try an agent and see what happens. You define the task, you run it through the matrix, you get an architecture decision with a rationale you can defend in a design review. Concrete. Usable today. But wait, knowing the framework is only half the problem. The other half is knowing how the two paradigms actually fail in practice, and that's what the next chapter covers. Here's what the end-state architecture actually looks like, the pattern that solves both failure modes at once. N8 sits at the orchestration layer. It handles all deterministic control flow, trigger conditions, routing logic, retry policies, error boundaries, cost circuit breakers. It knows every step in advance. It is auditable, versionable, and explainable to a non-engineer. Then, at specific decision nodes, where the task genuinely requires reasoning over ambiguous input, N8 calls out to a Claude agent as a bounded reasoning unit. The agent gets a scoped context, a defined output contract, and a hard token budget. It cannot spawn children. It cannot loop. It does its reasoning job and hands a structured result back to the orchestrator. N8 then takes that result and continues the deterministic pipeline. This is the hybrid pattern. The orchestrator provides the guardrails. The agent provides the intelligence. Neither is doing the other's job. This architecture kills cost blowouts because the agent has no autonomy over its own invocation cycle. And it kills rigidity traps because the pipeline doesn't do hard code every possible reasoning path. Delegates that to the model. This is not a theoretical pattern. It's running in production. And in the next chapter, we're going to break down exactly why both pure workflow and pure agent architectures fail, so you understand the forces this hybrid pattern is designed to absorb. Let me be direct about something most architects get wrong from the start. A deterministic workflow is not a dumb version of an AI agent. It is a fundamentally different contract with your production system. At its core, a deterministic workflow is a directed acyclic graph. Nodes are discrete operations, edges are fixed execution paths, and the entire graph is resolved at design time. There is zero ambiguity about what runs next. Node A always triggers node B. Node B always triggers node C. Execution path is a guarantee, not a suggestion. In NNA terms, you define this visually. Each trigger maps to exactly one downstream chain. The critical insight here is that deterministic is not a limitation. It is a promise you make to your ops team, your compliance officer, and your on-call engineer at 3 a.m. The system will behave identically on the 10,000th run as it did on the first. But here is the thing. That promise comes with a hidden cost that most teams don't discover until it's too late. So where does deterministic workflow genuinely win? I'm talking about real production wins, not marketing copy. First, business logic at volume. If you're processing 10,000 invoice PDFs per day with the same extraction rules, a DAG is exactly right. You don't need reasoning, you need throughput and predictability. Compliance audit trails. Every regulated industry I've worked with, fintech, healthcare, legal, needs a complete, time-stamped, immutable log of every decision step. A DAG gives you that for free, but the execution graph is the audit trail. Third, cost predictability. This is huge for startups. Your CFO can budget a workflow that runs 100,000 times per month because the cost per execution is flat and known. No surprise token bills. Fourth, trigger-based automation at scale. Webhooks, cron jobs, database change events, anything where the stimulus is structured and the response is procedural. Tools like N8, Zapier, and Temporal shine here precisely because the problem fits the paradigm. The anti-pattern I see constantly is teams reaching for an LLM agent to handle tasks that a 20-node N8 workflow would solve in a weekend, and they pay 10 times more in token costs for zero additional business value. But here is the edge case that breaks everything. What happens when the input isn't clean? Now let me show you exactly where deterministic workflows snap. I've seen this failure pattern in 3 different companies. The moment your input stops being clean and structured, the DAG becomes brittle. Imagine you've built a beautiful N8 in workflow. Customer email comes in, Rex extracts the order number, hits the database, response goes out. Then one customer writes, "Hey, I bought something last week. Not sure of the order number. Can you check?" Your regex finds nothing. Your lookup gets a null. Your workflow hits an unhandled branch and either silently fails or throws an unhandled exception that pages your on-call at 2 a.m. That's the edge failure. The second breakpoint is multi-step reasoning. If the correct next action depends on interpreting the meaning of previous outputs, not just their format, a DAG cannot express that dependency. You'd need to pre-enumerate every possible reasoning path at design time, which is combinatorially explosive. The third breakpoint is outshape ambiguity. When you can't define at design time what a valid output looks like, you can't build a deterministic validator node, so you ship without validation, and the downstream system gets garbage. These aren't theoretical failures, they are exactly what took down the production system I described in Chapter 1. Up next, the other side of the coin, and the costs are higher than you think. Now let's talk about the other paradigm, and I want you to hold on to every word here because this is where most teams overspend. An AI agent is as architecturally defined by a reasoning action loop, not a graph, a loop. The cycle goes like this. Perception, the agent ingests context, including the task, prior tool outputs, and memory. Planning, the LLM generates a next action based on that full context window. Tool execution, the agent calls an external tool. A web search, a database query, a code interpreter, an API. The agent evaluates the tool output and decides whether the goal is satisfied or another loop iteration is needed. Each one of these steps introduces non-determinism by design. The LLM's planning step is sampling from a probability distribution. The same input can produce different outputs across runs. The tool execution result feeds back into the context and shifts the probability distribution for the next planning step. This is not a bug. It is the architectural feature that enables agents to handle tasks that a DAG structurally cannot. Claude's managed agent framework, Autogen, they all implement variants of this same loop. The non-determinism is the feature, and this is the critical, but non-determinism in production without guardrails is not flexibility. It is controlled chaos. Let me show you exactly what that costs. Let me give you real numbers, because this is where budget conversations happen. I ran this comparison on a production support ticket classification system. The deterministic N8 workflow, regex classification plus a lookup table, costs roughly 0.01 cents per execution, runs in under 200 milliseconds, operational complexity is near zero. One engineer can maintain it indefinitely. The equivalent agent implementation using GPT-4 average 1,800 input tokens plus 400 out tokens per run. At current pricing, that's approximately 2 cents per execution, 200 times the cost. Average latency jumps to 3 to 8 seconds depending on tool calls. And operational complexity explodes. You now need prompt version control, token budget guardrails, loop iteration limits, tool call logging, and an evil pipeline to catch regressions. For the task of classifying a support ticket into one of 12 GURIs from structured metadata, the agent bought you exactly 0 additional capability. The flexibility premium was 200x cost for identical business output. Now here's where it gets interesting. There are tasks where that 200x premium is worth every cent. The question is whether your specific task is one of them, and most teams never ask that question rigorously. That's the trap. So what breaks when you pay that premium and still get it wrong? 3 failure modes. These are the ones that actually hit production. I have seen all 3 in real postmortems. First, goal drift. The agent reinterprets its objective partway through execution because an intermediate tool output shifts its context window probability distribution. Classic example, an agent tasked with summarize this support thread calls a search tool, finds related tickets, and returns a cross-ticket analysis nobody asked for. The output is technically coherent. The agent just drifted from the original goal. Second, loop accumulation. Without an explicit iteration cap, an agent that can't satisfy its goal criterion will keep looping. I've seen agents rack up 47 loop iterations and thalatebi in tokens on a single task before hitting a timeout. The fix seems obvious in hindsight. Always set max iterations, but under deadline pressure it gets skipped. Third, tool misuse. The agent calls a tool with a parameter combination that is syntactically valid but semantically destructive. A write-enabled database tool called with a where clause the agent hallucinated. This is not hypothetical. It is how a team I know wiped a staging database that had production data mirrored into it. The guardrails exist for all 3 of these, but you have to know the failure modes to implement the guardrails. Now, knowing both paradigms, the question is why teams keep choosing wrong. The answer is a framing problem, and it's the last thing we cover in this chapter. Here is the root mistake, and once you see it, you cannot unsee it. Every conference talk, every LinkedIn post, every vendor comparison frames this as AI agents vs workflow automation. Which one wins? Which one replaces the other? That framing is architecturally illiterate. It is the equivalent of asking whether a database or a message queue wins. They solve different problems at different layers of the same system. The real production question is never which paradigm is better. It is which paradigm governs which layer of this specific system for this specific task. I've reviewed architecture docs from over 40 engineering teams in the last 2 years. The ones that built fragile systems all shared one characteristic. They chose a paradigm at the project level, not at the task level. They said we are building an AI agent system, or we are building a workflow automation system, and then tried to force every task in the system to fit that single paradigm. The teams that shipped production systems made a different decision. They asked, for each task independently, how structured is the input? How bounded is the reasoning required? What's the acceptable cost per execution? And they mixed paradigms within the same system deliberately. The boundary between deterministic and probabilistic is not a technology choice. It is an architectural layer, and conflating the two is how you get a system that is simultaneously over-engineered and capable. Let me show you where that boundary naturally falls. Let me make this concrete with a spectrum. Think of automation tasks as a continuum from left to right. On the far left, fully structured data pipelines, fixed schema inputs, known transformation rules, predictable outputs, ETL jobs, invoice processing, database sync. Pure deterministic territory, a DAG is the only correct answer here. Moving right, structured inputs with conditional routing. Still deterministic, the branching logic is more complex. Customer onboarding flows with regulatory path selection. Still N880 territory, but more nodes. Middle of the spectrum, semi-structured inputs requiring interpretation. Customer support emails, product feedback forms, contract clause extraction. This is the boundary zone. You might need an agent to parse intent, but the downstream action should be a workflow. Right of center, multi-step reasoning with tool use. Research tasks, competitive analysis, dynamic report generation. Clearly agent territory, but the final output delivery should still be a deterministic step. Far right, open-ended autonomous reasoning. Self-directed research agents, code generation with self-debugging loops. Full agent territory, and frankly, most production systems should not be here yet. The paradigm boundary is not at the project level. It is at the task level, and it falls roughly at the boundary between structured interpretation and unstructured reasoning. Knowing exactly where your task sits on this spectrum is the prerequisite for every architectural decision that follows. And that's precisely what the decision matrix in the next chapter gives you. Let me anchor everything we've covered in this chapter before we move forward, because the next chapter builds directly on this foundation. Deterministic workflows give you a guarantee. Fixed topology, predictable execution, flat cost, immutable audit trail. Their failure mode is rigidity, They snap on unstructured inputs and multi-step reasoning requirements. AI agents give you flexibility, probabilistic reasoning loops, tool use, the ability to handle tasks that can't be pre-enumerated. Their failure mode is cost and reliability, goal drift, loop accumulation, tool misuse, and a 200x cost multiplier that most teams discover only after the invoice arrives. The root mistake is treating these as competitors. They are complementary paradigms that govern different layers of the same system. The paradigm boundary falls at the complexity axis, specifically at the point where structured interpretation ends and unstructured reasoning begins. Now, knowing that the decision is task level, not project level, you need a rigorous framework for making that call quickly, consistently, and without tribal knowledge. That is exactly what the 3-axis decision matrix in the next chapter gives you. 3 questions, any task, 15 seconds. The correct paradigm. Let's go. All right, so in the last chapter we saw how both paradigms, pure workflow and pure agent, each have their own specific failure mode. Now the question, how do you actually decide which one to use before you build anything? Because I've watched teams spend 2 weeks building a full agent pipeline, only to realize a simple N8 workflow with 3 nodes would have done the job. That's 2 weeks of engineering time gone. So let me give you the framework I actually use in production decisions. It's called the 3-axis decision matrix, and we're going to break down each axis one by one. The first axis is task complexity, and it's defined as the product of 2 things, ambiguity and output variability. Input ambiguity asks, how unpredictable is the shape of the data coming in? Output variability asks, how many different valid forms can the result take? You score each from 1 to 5. Score 1 on input means it's always a fixed schema, like a webhook payload you own. Score 5 means you're accepting free-form natural language with no structure whatsoever. Same logic on the output side. Multiply those 2 scores, and you get your complexity number ranging from 1 to 25. But realistically, most land between 1 and 12. But here's the thing most people miss. It's not just about whether the task is technically hard. It's about whether the ambiguity is irreducible, and that changes everything. Now let me make this concrete, because abstractions are useless without real examples. I pulled 12 tasks that come up constantly in automation projects and scored every single one on this axis. Look at the table. Slack notification routing, input is a structured event payload, output is a channel ID and message string. Ambiguity? 1. Output variability. 2. Score 2. This is a pure workflow job, full stop, no agent needed. On the other end, multi-source research synthesis, you're pulling from web search, internal docs, and unstructured meeting notes, and the output needs to be a narrative summary adapted to the reader's context. Input ambiguity, 4. 4. 4. Score, 16. That's an agent task. But here's what's interesting. Look at the middle of the table. Customer support ticket triage scores a 6, right on the boundary. And this is where teams fight. Half the team says just build a classifier, it's deterministic. The other half says but that the edge cases need reasoning. And both sides are technically right, which is exactly why we have the other 2 axes. The complexity score alone does not give you the final answer. It's just filter. So the practical threshold I use, and this is based on failures, not theory, is score 6 as the boundary line. Below 6, your default is a deterministic workflow, unless one of the other axes you to reconsider. Above 6, agent reasoning is required because the ambiguity cannot by static branching logic. Specifically, because in practice, anything with an input ambiguity of 3 or above starts breaking rule-based routers within the first 2 weeks of production traffic. I've seen this happen on 3 separate projects. You build the classifier, it works great on your test set, and then real users start submitting edge cases that don't fit any of your branches. At score 6, you're right at that inflection point. But, and this is critical, a high complexity score does not automatically mean you deploy an agent. It means you cannot use a pure deterministic workflow. There's still the determinism axis and the cost axis to check. A task can score 10 on complexity, but still require deterministic output because of regulatory constraints. And that tension between complexity and determinism is exactly what the next axis is designed to resolve. Now here's the axis that most architecture discussion completely ignore, and it's the one that has caused the most production incidents I've personally witnessed. Axis 2 is the determinism requirement, and this isn't a soft preference. For certain categories of systems, determinism is a hard contractual and legal obligation. I define 3 categories here. First, compliance-driven. These are systems where every execution must produce an identical, auditable, reproducible output. Think financial transaction processing, health data pipelines under PBA, or anything that gets touched by an external audit. The output must be the same given the same input, every time. No exceptions. Second, operationally driven. These systems where consistency matters for operational reliability. You need predictable SLAs and reproducible debugging, but a small degree of output variation is tolerable within a defined schema. Third, innovation-driven. These are systems where the whole point is generating novel, context-sensitive output, content generation, recommendation personalization, research assistance. Probabilistic output is a feature, not a bug. The critical mistake I see is engineers treating all three categories as the same engineering problem. They are not. And deploying an LLM agent into a compliance-driven context, even with good intentions, is an architectural liability that will eventually blow up in your face. Let me be very specific about which use cases fall into the hard determinism category, because I've seen teams rationalize their way into dangerous territory here. Fintech automation, payment routing decisions, fraud score calculation, transaction categorization for reporting, all hard determinism. Any deviation between runs on identical data is a compliance violation. Healthcare workflow, medication dosage calculation pipelines, diagnostic code assignment for billing, patent record routing, hard determinism. One wrong output that can't be reproduced for audit is a HIPAA problem. Legal document processing. Contract data extraction, where the extracted values feed into legally binding decisions. Hard determinism. And here's the thing, some of these tasks score high on the complexity axis. A complex financial transaction might 8 on complexity. But complexity does not override compliance. That's the trap. Engineers see the high complexity score and think this needs an agent. And technically, yes, the reasoning task is complex, but the output must be deterministic. So what do? That's exactly what the next scene covers. But first, understand this. If you deploy a pure agent in any of these contexts without additional guardrails, you are not making an architecture decision. You are making a liability decision. So what happens when a task scores high on complexity, meaning it genuinely needs agent reasoning, but also sits in the operationally driven or even compliance-adjacent determinism category? This is the scenario nobody writes blog posts about, but it comes up constantly in real systems. The answer is soft determinism, and it's a pattern I've used in production to navigate exactly this tension. The idea is straightforward. You wrap the agent call inside a validation layer. The agent does the reasoning, but before that output reaches any downstream system, it passes through a schema enforcement step. If the output doesn't match the expected schema, missing fields, wrong types, values outside allowed ranges, the system retries the agent call with a modified prompt that includes the validation error as feedback. You allow a maximum of 3 retries. If it still fails, you escalate to a human review queue. You do not silently fail and you do not pass bad output downstream. This pattern gives you agent-level reasoning capability with workflow-level output guarantees. It's not perfect. You still have non-determinism in the reasoning path. The output contract is enforced. In the next chapter, we'll see exactly how to implement this in a hybrid architecture with real code. But first, let me show you the third axis, because cost will override everything else if you ignore it. The third axis is the one that kills production systems slowly, cost and latency. And I mean slowly, because the cost impact of a wrong architecture decision doesn't show up on day 1. It shows up at the end of month 2 when your cloud bill is 3 times what's rejected and your CTO is asking uncomfortable questions. Let me give you real numbers. A single N8 in a workflow node execution costs effectively nothing, fractions of a cent, mostly infrastructure amortization. A single code haiku call for a simple classification task, maybe 200 input tokens, 50 output tokens, costs roughly negligible. But a Claude Sonnet multi-step agent solving a research synthesis task. 3 tool calls, 2,000 in tokens per call, 500 output tokens per call. That's closer to evil per execution depending on the model version and tool use multiple players. Now those numbers look small in isolation, but run the math at volume. 10,000 executions per day of that agent task. You're looking at $2 per day. $2,000 per month. For one automation task, I've walked into 2 startups where the CEO had no idea their agent pipeline was burning that much until they got the AWS bill. The architecture was technically correct. The cost model was completely wrong. Latency is the other side of this. Workflow node, under 100 milliseconds. Single LLM call, 500 milliseconds to 2 seconds. Multi-step agent with tool calls, 5 to 30 seconds. If your task is user-facing and synchronous, that 30-second wait is a product failure, not just a technical concern. So how do you make the cost decision rigorous instead of just going with your gut? I use what I call the cost ceiling rule, and it has 2 parts. Part 1. If a task runs more than 1,000 times per day, agent cost must be explicitly justified. Not assumed, justified. The justification requires you to measure a quality delta. What is the measurable improvement in output quality that the agent provides over a deterministic workflow? And then the multiplier. That quality improvement must save at least 10 times the cost in downstream errors, rework, or escalations. Otherwise, the agent is burning money to solve a problem that a cheaper architecture could handle. Let me make this concrete. Susan costs 0.0 cents per run and runs 5,000 times per day. That's 500 per day. 1,000 per month in agent costs alone. For that to be justified, the agent's better output quality must be preventing at least 50 per month in downstream damage, customer churn from bad recommendations, manual rework hours, escalated support tickets, whatever your failure mode is. If you can't draw that direct line with actual data, you don't have a justified agent deployment. You have an expensive prototype masquerading as production infrastructure. And the second part of the rule, even if cost is justified, if your latency SLA is under 2 seconds for a user-facing task, a multi-step agent is architecturally disqualified unless you've pre-computed or cached the reasoning. No exceptions. I've tried to argue with this rule. I always lose. Now let's put all three axes together into the final decision matrix. You score your task on complexity, 1 to 25. You classify its determinism requirement, hard, soft, or probabilistic. You check its cost and latency profile against the ceiling rule. And the matrix outputs one of exactly 4 architecture recommendations. First, pure workflow. Low complexity hard determinism, or high volume below cost ceiling. Use N8 Zapier or any deterministic orchestrator. Fast, auditable. Second, pure agent. High complexity, innovation-driven determinism, cost justified at volume or low volume. Use Claude-managed agents or equivalent. Full reasoning capability except the cost and latency. Hybrid orchestration. High complexity, operationally driven determinism, medium volume. Workflow orchestrates the overall pipeline. Agent handles specific reasoning subtasks. This is the most common real-world outcome, and it's what the next chapter covers in full detail. Fourth, hybrid with guardrails. High complexity, compliance adjacent, or soft determinism, cost justified. Agent wrapped inside a validation layer, schema enforcement, human escalation path built in. This is the soft determinism pattern we just saw. Here's the honest truth after 24 years. Most real enterprise automation tasks land in category 3 or 4. Pure workflow is for simple tasks. Pure agent is for genuinely open-ended reasoning. Everything in between, which is the majority of what you'll actually build, requires a hybrid approach. And in the next chapter, I'm going to show you exactly how to build that hybrid architecture with real implementation patterns, because the matrix tells you what to build. The next chapter shows you how. All right. So in the last chapter, we walked through the 3-axis decision matrix and figured out when to use an agent versus a deterministic workflow. Now, hard part. How do you actually wire these two worlds together without blowing up your architecture? Here's the pattern I keep coming back to after trying everything else the hard way. An AIM, or whatever orchestrator you're using, owns the outer shell. It handles routing, retries, logging, and error boundaries. That's its job, and it's genuinely good at it. The AI agent, Claude in our case, gets invoked only at specific nodes where real reasoning is required. Think of it, a surgical cut. You're not handing the whole workflow to the agent. You're calling the agent at exactly the moment the deterministic path hits a wall. This is the orchestrator-agent pattern. The orchestrator is the skeleton. The agent is the muscle at the joint. Most people I see get this backwards. Put the agent in charge of everything and wonder why they can't reproduce bugs. Don't fall into that trap. But here's the thing, knowing the pattern is easy. The API boundary design is where everything actually falls apart. Let me get specific, because call the agent at the right node is still vague enough to cause disasters. When N8N hits an agent node, it needs to hand off context in a structured way, not free-form text, a contract. Think of it like a typed function signature. You pass in a task description, the relevant context payload, capped, not the entire up history, and an output schema that the agent must conform to. On the Claude side, the system prompt encodes the behavioral contract. The user message carries the runtime context. And critically, you force structured output. You're not parsing prose, you're consuming a JSON object with defined fields. Then on return, before N8N does anything else with that data, you validate the output schema. I've seen workflows silently pass a malformed agent response into a database write, because nobody added that validation step. Production incident. Real data corruption. The lesson. Treat every agent response like untrusted external input. Because functionally it is. The API boundary is a trust boundary. What happens when the agent doesn't respond at all? 3 patterns. Non-negotiable. If you skip any of these, you will have a production incident. I'm not guessing, I'm telling you from scars. First, idempotent invocation. Agent call must be safe to retry with the same input and produce the same downstream effect. If your agent writes to a database, you need an idempotency key. Otherwise, a retry on timeout becomes a duplicate record. Second, hard timeout with fallback. Never let an agent block your workflow indefinitely. Set a hard wall. I typically use 15 to 30 seconds, depending on the task. If the agent doesn't respond within that window, route to a deterministic fallback path. Not an error page, a working fallback. Third, output validation before propagation. We just covered this, but it bears repeating as a hard gate. No downstream node should ever receive an agent response that hasn't passed schema validation. These three form your safety net around every agent node in the system. Get right, and your hybrid architecture is resilient. Skip one, and you're one weird LLM response away from a cascading failure. Next up, Claude-managed agents just changed some of these assumptions, and not in the way you'd expect. Okay, so Anthropic released Claude-managed agents, and a lot of people in my network had one of two reactions. Either this changes everything, or this is just a wrapper. Both are wrong. Let me tell you what actually changed and why it matters for your architecture decisions. Before managed agents, if you wanted Claude to use tools, search, code execution, API calls, you built the agent loop yourself. You handled tool routing, you managed the back and forth turns, you tracked the execution context across calls. That's not trivial code. It's also a significant failure surface. Managed agents introduced three concrete things. A managed execution context that persists across tool calls within a session, native tool routing, where Claude decides which tool to invoke, and Anthropic's infrastructure handles the call dispatch, and session-level memory that doesn't require you to reconstruct context on every API round trip. The integration contract with your orchestrator changes here. You're no longer calling Claude per turn and managing state yourself. You're opening a managed session and letting it run to completion. That's a fundamentally different model. And it has implications for how N8 talks to it. But here's the part that surprises people. The advantages come with a specific set of trade-offs you need understand before you commit. Let me put some numbers on this, because the comparison gets real interesting when you're actually maintaining the system 6 months later. Building a custom agent loop from scratch, I've done this twice now, means you're writing somewhere between 300 and 800 lines of agent loop logic. Tool registration, retry on tool failure. Context truncation, when you approach the context limit, turn management, error classification. Every one of those is a bug surface. With Claude-managed agents, that collapses to roughly 40 to 80 lines. You register your tools, open a session, send the task, and consume the result. The failure surface shrinks dramatically because you're not writing the orchestration logic inside the agent anymore. Operational burden also shifts. You're not on call for your agent loop crashing at 3 a.m. because context management hit an edge case. Anthropic is handling that runtime. Now, before you immediately migrate everything, the reduced lines of code come with a cost that doesn't show up until you're in production. And that cost is the topic of the next scene. But seriously, if you're currently maintaining a custom agent loop, and it's more than 200 lines, you owe it to yourself to run this comparison. Here's the part Anthropic's documentation won't highlight for you. Managed agents introduce trade-offs that only become painful after you've committed. First, portability. Your tool registrations, session management calls, and execution model are now coupled to Anthropic's API shape. Switching to a different model provider, say in a year, when the competitive landscape looks different, means rewriting more than just the model call. You're rewriting your execution model. Second, execution trace opacity. With a custom loop, I can log every turn, every tool call, every intermediate state. With managed agents, the execution inside the session is partially opaque. You get input and output. The intermediate reasoning steps require explicit trace configuration that may not expose everything you need for debugging a production failure. Third, and this is the sneaky one, context window management responsibility doesn't disappear, it shifts. You're trusting Anthropic's truncation strategy. If their strategy doesn't match your task requirements, you might get silently degraded outputs with no error signal. Before you commit to managed agents, verify 3 things. Do you need full execution trace access for compliance? Do you need model portability within 18 months? And do you have task-specific context management requirements? If yes to any of those, design your abstraction layer carefully. Coming up next, we put all of this together into a reference architecture you can actually hand to your team. All right, let's assemble everything into a concurrence architecture you can actually whiteboard with your team tomorrow. Here's the end-to-end flow, layer by layer, with each layer's responsibility explicitly named. Layer 1. Event trigger, webhook, cron, message queue event. It lands here. N8 catches it. Nothing smart happens yet. Layer 2. N8 routing layer. This is pure deterministic logic. Route by event type, payload shape, source system. No AI touches this. Layer 3. Classification node. This is your first decision gate, and it's where Axis Matrix from Chapter 3 applies. Is this task deterministic enough to route straight through, or does it need reasoning? This nogs that call, and it can itself be a lightweight classifier, not necessarily a full agent. Layer 4, deterministic path or agent node. If the classifier route's deterministic, you execute a predefined N8N sub-workflow. If it routes to agent, you invoke Claude via the API boundary pattern we just covered, structured prompt, output schema, the whole contract. Layer 5, output validation. Every path, deterministic and agent, passes through schema validation before anything goes downstream. Layer 6, downstream system write. Database, API notification, whatever the business outcome is. This is where the value lands, clean, validated, auditable. Now, this architecture has no observability layer yet. And that's the next thing we're adding, because without it, you're flying blind on cost and correctness. Here's something I learned the expensive way. A beautiful architecture with no observability is just a black box with good diagrams. You need to see what's happening at every layer in real time. And most importantly, you need to know when an agent node is burning money before it becomes a billing surprise at the end of the month. Here's what the observability layer looks like when bolted onto this reference architecture. At the orchestration layer, N8N8 gives you execution logs per workflow run. Use them. Tag every run with a correlation ID, so you can trace a single event across all nodes. At the agent invocation layer, log 3 things per call: the input token count, the output token count, and the wall clock latency. This is your cost accountability data. Aggregate this per workflow, per agent node, per day. Set alert thresholds. I use a per day token budget per workflow as my primary alert. When a workflow starts consuming its baseline tokens, something is wrong. Either the context payload grew unexpectedly or the agent is looping. Catch it before it hits your invoice. At the output validation layer, log validation failures separately with the raw agent output. These failures are your leading indicator of prompt drift. When the agent starts turning responses that don't match your schema, your prompt needs attention. This observability layer is not optional. It's what separates a production system from a prototype. Let's land the plane on this chapter with 3 governing principles that should be carved into the wall of every team building hybrid AI workflow systems. Principle 1. Determinism at the orchestration boundary. Your workflow layer must behave predictably on every execution. Triggers, routing, retries, error handling, these are not places for probabilistic behavior. Lock them down with deterministic logic and keep the AI out of them. Principle 2. Reasoning only where it earns its cost. Every agent node costs money and introduces latency and uncertainty. Before you add one, ask, what does the agent provide here that a deterministic rule or a classifier cannot? If you can't answer that clearly, the agent doesn't belong there. This is the anti-pattern trap the lecture title warned you about, putting agents everywhere because they seem powerful. Principle 3. Every agent call must be observable and recoverable. No agent invocation should be a black box inside your system. You log it, you measure it, you can replay it, and you have a recovery path when it fails. These 3 principles are not abstractions. They are the operational guardrails that separate a hybrid architecture that scales from one that quietly grades in production over months. In the next chapter, we move from architecture to real war stories, production failures that happened because someone violated exactly these principles. Things get very specific very quickly, and some of it will be uncomfortable. Let me tell you about a Friday afternoon I never want to repeat. We had an agent tasked with research and summarize competitor pricing until complete. Sounds simple, right? The problem was that complete was never defined. The agent started summarizing, then decided it needed more data, created subgoals to validate that data, then created subgoals to validate the validation, and it just kept going. 23 minutes, $340 in API costs. Our circuit breaker finally killed it, but by then the damage was done. Here's the brutal truth. The agent wasn't broken. It was doing exactly what we told it to do. We just never told it when to stop. Vague success criteria are not a prompt engineering problem. They are a systems design failure. And this pattern shows up in almost every team's first serious agent deployment. The scariest part? It will happen again unless you build the stop condition into the architecture itself, not just the prompt. Now let me show you exactly what the fix looks like. So what do you actually change after an incident like this? 3 things, and they operate at different layers of your stack. First, at the prompt level, you're a single, binary, verifiable success criterion. Not research until complete, but return exactly one JSON object with fields X, Y, Z. Stop after the first valid response. The agent needs to be able to ask itself, am I done yet? And get a yes or no answer. Second, at the orchestration layer, you enforce a hard step budget. In N8N or LangGraph, you set a maximum iteration count. I use 10 as a starting default. And if the agent hits that ceiling, the workflow terminates and pages the on-call engineer. Not graceful degradation. Hard stop. Third, at the infrastructure layer, a token-based circuit breaker that is completely independent of the agent logic. It watches total token consumption per run and kills the process if it crosses your threshold. The key insight here is that these three defenses are redundant by design. Any one of them should catch a runaway before cost spiral. If all three are in place and one fails, the next one catches it. Defense in depth, the same principle you apply to security, applied to agent cost control. And wait until you see what happens when you skip the schema validation layer. The damage is silent, and by the time you find it, it's already too late. This next one is the failure mode that keeps me up at night, because it doesn't announce self. No error logs, no alerts, no spike in API costs. Everything looks healthy while your data quietly turns to garbage. Here's what happened. We had an agent extracting structured data from documents and passing it downstream. The model provider pushed an update. No breaking change notice, just a model update. The output format shifted slightly. A nested field flattened. A date string changed time zone representation. Our downstream workflow consumed it silently, wrote it to the database silent, and moved on. 6 hours later, a data analyst flagged anomalies. We pulled the logs. 2,400 records corrupted. The rollback took 4 hours. The reprocessing took 2 days. And here's the thing that made it worse. We had unit tests for the agent. The tests passed, because our tests were validating the old format against the old model, and the model had changed underneath us. This is what I call a silent failure. The system tells you everything is fine, right up until a human looks at the actual data. The works in AI systems are not the ones that crash. They are the ones that smile and keep running. The fix is a 3-layer defense, and each layer catches a different failure mode. Layer 1. Structured output mode at the API level. If you are using GPT-4o or Claude, you use their native JSON mode or function calling response format. This forces the model to output valid JSON that conforms to your schema. It cannot drift because the API itself's non-conforming responses. 2. JSON schema validation at the workflow node. Every node that consumes agent output runs the payload through a schema validator before passing it downstream. Fail fast, fail loudly. Do not let malformed data travel one step further in your pipeline. If validation fails, the workflow halts and fires an alert. Layer 3. And this is the one most teams skip, model version pinning with a canary update policy. You pin your production workflow to a specific model version, not the latest alias. When the provider releases a new version, you run it in parallel on 5% of traffic with enhanced schema monitoring for 48 hours before promoting. Same principle as a deployment canary, you already know how to do this for code. Now apply it to models. The dirty secret of the AI industry is that latest is not a model version, it is a liability. Pin your models like you pin your NPM packages. And if you think this level of engineering is overkill, wait until the next section, because the pendulum swings the other way too. Alright, I have spent 2 sections telling you what breaks when agents are under-constrained. Now let me tell you about the opposite failure, and in some ways, this one is more embarrassing, because it comes from enthusiasm. A team on a project I was consulting for had a perfectly working workflow. 3 nodes. Parse a structured JSON payload from a webhook, transform a field, post to Slack. It ran in under 200 milliseconds, cost essentially nothing, and had been in production for 8 months, without a single incident. Then they attended an AI conference. 2 weeks later, they had replaced it with a full Claude agent. It will be more flexible, they said. The agent now takes 1,600 milliseconds. It costs 4 cents per run, which doesn't sound like much until you do the math at their volume. That's over $4,000 a month for a task that previously cost $12 a month. And what does the agent decide? It decides to parse a structured JSON field, a field that never changes format, a field that a regex handles in 3 lines. There was no ambiguity. There was no reasoning required. There was no decision that a deterministic function could not make. They paid an 8x latency penalty and a 350x cost increase to add an LLM to a problem that didn't need one. This is the complexity tax, and it's more common than any of the failures I've described today. So how do you avoid the over-engineering trap before you build, not after? I use what I call the agent justification test, and it takes 30 seconds. Before you deploy an agent, you must complete this sentence out loud. This agent is necessary because it needs to decide blank, and a deterministic function cannot make that decision because blank. Both blanks must be filled. If you cannot complete the sentence clearly and specifically, you do not have an agent use case. You have a workflow use case wearing an AI costume. The default should always be the deterministic workflow. Agents are the exception, not the rule. You reach for an agent when you have genuine ambiguity, unstructured inputs, branching logic that depends on content meaning, or multi-step reasoning that cannot be encoded as a decision tree. The decision rule this If you can write the logic in code, write it in code. If the logic requires understanding, reach for an agent. And here is the most important principle I can leave you with from all three of these battle stories. Every failure I described today was preventable. Not by using better AI, by applying better engineering discipline to the layer around the AI. We have spent this entire chapter in the trenches. In the next chapter, we take everything, the hybrid architecture, the failure modes, the cost analysis, and we build the complete decision framework you can use on your next project, starting tomorrow. All right, let's be brutally honest. After 5 chapters of war stories and framework theory, you might still walk away and make the exact same mistakes I did in year 3 of my career. So let's lock in the 8 anti-patterns I see often in production reviews. 4 from over-agentifying, 4 from under-leveraging. Don't wrap a simple REST call in an agent loop just because the task sounds smart. Use a deterministic workflow node instead. It's faster, cheaper, and debuggable in 30 seconds. Don't give an agent write access to production databases without a human-in-the-loop gate. Isolate write operations behind a confirmed workflow step with rollback logic. Don't chain 5 agents together when 1 orchestrator and 3 deterministic tools would solve it. Map your dependency graph first. If it's a DAG, it's a workflow, not an agent swarm. And here's the one that kills startups. Don't skip observability because we'll add it later. Wire your token usage, latency, and decision trace from day one. On the other side, don't hardcode every branch of a complex classification pipeline. Let an agent handle the ambiguous edge cases while the deterministic path handles the 80% to happy path. The pattern is always deterministic by default, age by exception. But here's the uncomfortable question. How do you know before you build which category you're actually in? Now here's the tool I wish I had back in 2019 when I was 3 weeks into building an agent system that turned out to be a fancy if-else tree. This is the 7-question pre-build checklist. Run through this before you write a single line of automation code. Question 1. Can I express the full task logic as a deterministic DAG? If yes, default to workflow. Question 2. Does this task require real-time external context that changes the execution path at runtime? If yes, agent is justified. Question 3. What is my cost ceiling per execution, and have I calculated the worst-case tokens? If you can't answer this, stop right now. Question 4. What is my failure blast radius? If this node halts, what goes down with it? Agents fail silently and expensively. Workflows fail loudly and cheaply. Question 5. Do I have end-to-end trace logging for every decision branch? No trace, no production. Question 6. Have I defined the human escalation path for confidence below threshold cases? Question 7. And this is the one most CTOs skip. Who owns this system in 6 months? Can they debug it without reading your Slack messages? If the answer is no, you've built a liability, not an asset. Run this checklist in your architecture review. Make it a team ritual. The teams that skip this checklist are the ones filing incident reports at 3 a.m. And I've been on both sides of that call. Theory without action is just entertainment. So here are your 3 concrete next moves, not someday, this week. First, pick one existing automation system you own right now. Pull up the 3-axis matrix we covered in Chapter 2. Complexity, determinism requirement, operational cost. Score that system honestly on all 3 axes. I guarantee you will find one node that's in the wrong paradigm. It might be an agent doing a job that a cron job and an API call could handle for 1/10 the cost. Or it might be a brittle rule engine trying to classify documents that an agent with 2 tools would handle in 3 lines. Second, identify the single highest complexity decision node in that system. That's your highest risk point. Ask yourself, is this node agent-driven because the task genuinely requires it, or because someone defaulted to the shiniest tool available at the time? Third, run the pre-build checklist on that node retrospectively. If it fails questions 3, 4, or 5, cost model, blast radius, observability, you have an action item for your next sprint, not your next quarter. I've done this audit with 6 engineering teams in the past year. Every single one found at least one critical misalignment in the first pass. The question isn't whether your system has this problem. The question is which node it's hiding in. And you're about to find out. Let me leave you with the 5 sentences that replace 2 years of painful trial and error. 1. Agents and workflows are not competing tools. They are complementary paradigms that solve fundamentally different problem shapes. 2. The decision axis is always task complexity versus determinism requirement versus operational cost. Never hype, never tool loyalty. 3. Deterministic workflow is your default. Agent autonomy is your exception, justified only when runtime ambiguity genuinely cannot be resolved in advance. 4. Every production-ready automation system needs cost ceilings, blast radius maps, and end-to-end decision traces before the first deployment, not after the first incident. 5. The architect who survives is not the one who picks the best tool. It's the one who picks the right paradigm for the right problem and can explain that choice to a new engineer at 2 a.m. during an outage. And the single principle that prevents every failure mode we covered in this entire lecture. Complexity belongs in the architecture decision, not in the runtime execution. If your system is complex at runtime, your design didn't do its job. That's the trap. That's what this whole lecture was about. Now you have the framework. Go audit something real. And come back and tell me what you found.